The second talk in the session is from a former PhD intern of mine. Qiuyu is a student of Mike Reiter at the University of North Carolina. He's going to present some work that he did largely this summer at VMware. The title of the talk is Encrypting OVN Tunnels with IPSEC.
Hi everyone, my name is Qiuyu, and today I'm going to talk about encrypting OVN tunnels with IPSEC. So this work I've done for the summer, and there were some previous work on IPSEC. I extended those to make it work on OVN. So first I will talk about the IPSEC support in OVS, and then I will talk about how OVN uses the IPSEC support to encrypt its traffic, its tunneling traffic. So first, let's talk about the motivations, like why do we need the encryption? So, well, the virtual machines running in the cloud might compute and communicate many sensitive data, like financial data or health data, so you don't want this data being accessed by unauthorized users or even attackers. So we needed to protect those kind of data. And the secondary is a physical network devices like router and switches cannot be trusted or might be compromised. So there are many such scenarios, like the traffic across data centers might go through untrusted routers, and also the router misconfiguration might direct your traffic to some unintended location. And the attackers might also break into your internal network and have access to your internal network devices. And also, like the administrators might being social engineered to reveal their password. So in these cases, like this traffic are not as secure as we thought. And the second bigger motivation is IPSEC configuration is actually very complicated. So there are many configuration fields. IPSEC itself has two modes, which is tunnel mode and transport mode. And you can also choose different cryptographic algorithms and parameters for doing the encryption. And also, like for different IKE daemons, the configuration interface are different. So it's just not easy for a normal network administrator, which doesn't have a lot of security background, to figure out all those different fields and make the right configuration. And what's worse for this kind of security configuration is like you will only know that your configuration is incorrect until some bad thing happens. So it's not very easy to verify whether I have a correct configuration or not, except for reasoning through the encryption parameters you have chosen, or the algorithms you choose to deploy. So in this project, we aim to offer an easy-to-use interface for the administrator to configure IPSEC encryption for the tunnel traffic in OVS. So, and in a very high level, for tunnel packets, so there are outer Ethernet header, outer IP header, and a tunnel header, and then there are inner headers. So the tunnel header could be GENEVE, VXLAN, or GRE. So if it's GENEVE or VXLAN, then there is also UDP header, like after the outer IP header. I omit those details, just want to demonstrate this concept. So with IPSEC encryption, everything up above the outer IP header is encrypted. So with the encryption, you get confidentiality, integrity, and authenticity. So the attacker won't be able to look into the contents of your data. They cannot change it. And you also know that the data I received is from some authenticated and trusted remote host. So before I talk about how OVS adds the IPSEC support in implementation, I would like to give a little bit more background on IPSEC in Linux. So basically, the IPSEC implementation in Linux comprises of 2 parts. The first part is IK daemon. So the IK daemon runs in user space, and it runs the IK protocol to each host will has IK daemon running in such host. And the second part is the IPSEC kernel stack. It's running in the kernel space. So the IK daemon runs IK protocol, and it does authentication. So it authenticates another host's identity, and it negotiates the cryptographic algorithms both hosts wants to use. And after the negotiation, it generates the key material, the symmetric key, which is going to be used later for symmetric encryption and cryptographic hashing. After the IK daemon finished the negotiation part, it installs the security policy and the security association into the kernel. So the security policy basically tells which traffic the IPSEC is going to protect. So it matches on different, based on different fields of your IP packets to decide whether I want going to protect this IP traffic or not. And the security association contains the cryptographic algorithms you're going to use, and also the symmetric keys. So with the security policy and the security association, the IPSEC kernel stack then matches IP packets and does encryption and decryption. It also then checks the integrity and the authenticity of the packet. So the protocol for doing that is ESP and the AH protocol. So for OVS-IPSEC, basically we reuse the IK daemon and also the Linux kernel IPSEC stack. What we add in the OVS-IPSEC is we add a OVS-IPSEC daemon. So the daemon sits between the OVS-DB and the IK daemon. The configuration for OVS-IPSEC is done in the OVS-DB. So like the administrator can do the configuration with the same tool and in the interface they're familiar with. We have 3 different authentication mode for the administrator, for the user to choose. So the first authentication method is by using a pre-shelled key. So for pre-shelled key, basically in 2 hosts, which wants to build a IPSEC tunnel, so they choose a shelled secret called the PSK, and then they use the OVS VSCTL command. Then specify it for a specific tunnel in the options field by saying what's the pre-shared key value. So if 2 hosts they have the same pre-shared key, then they can authenticate each other. So this method is very easy to use, but it's also less secure, because if the attacker figures out what's the pre-shared key, like the attacker then can impersonate the remote host to basically trick the local host. So in the second authentication mode, you can use the self-signed certificate. So in the self-signed certificate approach, each host first needs to has its own certificate and private key. So this certificate can be self-signed, and it first in the open vSwitch table, it specifies what's the local file system path of the certificate and the private key. And then it also needs to download the certificate of the remote host to the local file system and specify the remote certificate of the remote host. So after this configuration, only if the remote host can present the associated private key of that remote certificate, will this remote host be trusted by the local host. So this configuration works and is secure, but the problem is, like, if we have many hosts, then each host builds tunnel with each other, then we have to download all the certificates of other hosts in the local file system. So a better way, so here comes a better solution. We can, the user can use a CA signed certificate to do the configuration. With a CA signed certificate, each certificate is signed by a CA, the private key of a CA, and it downloads the CA certificate is downloaded in the local file system, and the local host specifies the path of its own certificate, private key, and the CA certificate. And then in the tunnel configuration field, the user specifies what's the remote name of the host we trusted. So this remote name is the common name of the certificate of the remote host. So in this configuration mode, the local host doesn't have to download the certificate of the remote host. So if the remote host can present a private key of a certificate which is signed by the CA's private key and also has the common name of this specified common name, then this authentication step can succeed. So the user does configuration in the OVS-DB, and the OVS-IPSEC daemon monitors the OVS-DB. And if it finds that some tunnel is configured to be IPSEC tunnel, then it basically does the translation. It then configures the IKE daemon by using the configuration file of the corresponding IKE daemon. Then the IKE daemon sets up a security policy and the security association, and install those to the IPSEC kernel stack. So here, this is an example. So suppose the user wants to use IPSEC to encrypt the GENEVE tunnel, and it chose the authentication method he wants, and the policies, these policies matches based on the UDP and also the source port and the destination port of the UDP field. So the port number is 6081. So that's actually the used in the GENEVE tunnel packet. So after that, every packet coming out from this tunnel goes to the IPSEC kernel stack, and the IPSEC kernel stack encrypts it before sending it out, and also do some cryptographic hash and send it out. For the incoming encrypted packet, it decrypts it and also verifies the integrity and authenticity of the encrypted packet and delivers it to the OVS data path. So what we achieve here is for the user, it only has to configure the OVS DB, and the configuration is basically selects which tunnel it wants to protect, and then makes the authentication configuration by either using pre-shared key or certificate. And that compared with configured IKE daemon, the configuration interface we offer here is much simpler. So OVN uses the IPSEC. So OVN itself uses OVS to tunnel its traffic, overlay traffic, and so it directly uses the OVS-IPSEC support. So here is overall architecture of OVN. Basically, the northbound database and contains logical network information, and the southbound database contains some physical network information, for example, the location of the logical port. So in each hypervisor, there is a OVS instance and the OVS DB, and also there is an OVN controller deploys rules to those OVS bridges. The OVN controller interfaces with the southbound database. In OVN IPSEC, we use the CA-based authentication because potentially each hypervisor might want to build a GENEVE tunnel with all the other different hypervisors. So it's just not easy to get all the certificate in the local hypervisor if you want to use self-signed certificate to do the authentication. So what you will do in OVN IPSEC is for each hypervisor, you get a certificate and a private key, and you create a CA, use the CA private key to sign those certificates, and configure those certificates in the local hypervisor. If you want to enable the IPSEC encryption, you just need to use the OVN northbound NBCTL command to set the IPSEC field as true in the northbound NB global table. So if the IPSEC is turned on, then all the tunnel traffic, all the GENEVE tunnel traffic will be encrypted. And if you turn it off, those traffic will not be encrypted by IPSEC. I did some evaluation to test the performance of IPSEC. So as you can imagine, like the encryption will give some performance degradation. And I use StrongSwan as the IKE daemon and test it in Linux 4.4 and Xeon 2 processor. The 2 hypervisor is connected with a 10 Gbps NIC. I use iPerf to generate TCP string in a default setting with window size 85 kilobytes. So here is the result. So without encryption, the throughput can easily achieve 10 Gbps, close to 10 Gbps. If we use AES 256, SHA-256 encryption, it's around 500 Mbps, the throughput. AES GCM is a faster encryption algorithm, and it can achieve the throughput can be 2 Gbps. So the computation is mostly CPU bounded. For both encryption algorithms, the CPU usage of the client is close to is around 90%, and without encryption, it's only like the client is only 20%, and the server is only 40%. So here is the current status of OVS-IPSEC. The IPSEC daemon is compatible with both StrongSwan and LibreSwan IKE daemon, and there are packages for Ubuntu and Fedora, so you can just install that package in your system. I also wrote some tutorials on how to use OVS and OVN IPSEC. In order to use it, you need to use the OVS out-of-tree kernel module. And there are some possible extensions for this work. So basically, we can have some more flexible tunnel encryption policies. We can only, the administrator can say we only want to encrypt the tunnel traffic between certain hypervisors instead of all hypervisors in OVN, so that only the hypervisors sitting in different data centers, only the tunnel traffic between those hypervisors will be encrypted. We can also potentially specify that only the traffic from certain logical network will be encrypted, because there are virtual machines which runs more sensitive computation than other virtual machines. So we can put them into the same logical network, and only the traffic between those virtual machines will be encrypted. So other virtual machines, the traffic from other virtual machines won't be encrypted. So we get less performance penalty. Okay, I finished my presentation, and I'm ready for questions.
All right, let's thank the speaker.
I know for IPSEC session, you need to set public certificate and private certificate, right? But in your slides, you only one other configure option for this.
You mean we needed to set up a public certificate and also a
private certificate?
No. So each certificate has associated a private key. So you needed to. Yeah, you needed to specify the certificate under the private key.
Yeah, but here you just use one certificate, right?
Yeah. So
for different tenant networks, how do you handle different tenant session?
So I think so. This certificate is basically represents the identity of the host.
Okay.
So only one certificate is needed. If it's a CA side certificate, you also need a CA certificate.
Okay, a CA certificate just to verify this case. Right?
Yes, the purpose of CA certificate is to verify the authenticity of the certificate of the remote host.
Okay, so here your certificate name is confusing. Here it's VM, right?
Oh yeah. I should have put it as the host one. Yeah.
So for one hypervisor, just one certificate.
Yeah, one hypervisor, one certificate.
Okay, got it.
Yeah. Sorry, it's a little bit confusing.
Okay, got it.
Yeah.
Thank you.
Hi.
No? Okay. Am I on? So thanks for putting the Fedora package and the other Ubuntu package in there, so that's awesome. But you said that you needed an out-of-tree kernel module?
Yes.
Could you explain why is that?
So the reason for that is in order for the IPSEC kernel stack to match which traffic to protect based on the security policy, it needs to parse the UDP port number for GENEVE tunnel and also for VXLAN tunnel. And for VXLAN, there is for the upstream kernel module, it works in VXLAN, but it doesn't work for GENEVE because when the IPSEC kernel stack gets the packet, like it doesn't have the port information in the function call. So basically, we need to add a patch for that.
Okay, maybe we can work together to fix that problem. So let's talk offline.
So I believe that the patch for that has already been submitted upstream.
Okay.
Do you know whether it's been accepted?
I actually haven't checked that, but yeah.
Yeah, we've had Greg on our team.
Okay.
I think that he's been taking that over. These are small patches, right? A couple
Yeah,
lines
it's
of code.
small patch.
Okay.
It's just 2 lines of
Awesome.
change. Yeah. So
Cool.
yeah, if you only want to encrypt VXLAN or GRE tunnel, you don't need this out of tree
Awesome.
module. Yeah.
So there's plenty of hardware companies here, Mellanox, Metronome, Intel. Maybe we can collaborate with them for the offloading of this stuff also. Easy offloading. Shameless plug, if possible.
Yes.
So one short question is, you mentioned about VXLAN GENEVE, so does that support STT too for the encryption?
Yeah, STT is also supported.
Okay, thanks.
Yes.
Regarding the encryption, you doing encryption only on the IPSEC, IPSEC of the tunnel.
Yes.
Did you look maybe to have encryption on the inner and different encryption per VM?
Sorry.
The concept you suggest is that the encryption is happening between two between hypervisor.
Yes.
Did you try also to look on a concept that's the encryption tunnel is on top of the VXLAN, is in between the two VMs?
You mean the encryption is done inside the VM?
Yeah, it's not inside the VM, it's on behalf of the VM, like encryption as a service.
Yeah, so, I mean, if you create a tunnel which tunnels traffic between 2 ports, and those ports are VM ports, then you can just simply in the configuration database say, I want to add the IPSEC encryption for this tunnel. Then the traffic between these 2 VMs are encrypted.
Yes, but you want to use a different key between 2 different. You could have 2 servers. On each server, you have 2 virtual machines.
You mean you want to use different keys for different pairs of virtual machines?
Yeah.
Do you mean the key? I think it's, so
You want to have a different.
Yeah, in the host, you only have 1 key, 1 private key for 1 host. But but I believe for different IPSEC session, there are different symmetrical keys.
Right.
So one possible issue with having separate key pairs per VM would be that you would presumably have to migrate those along with the VM if the VM migrated. It's not ideal to move around private key data.
Yeah, but then you get the encryption as a service, encryption for the VM, and not just encrypting the traffic between the hypervisor. It's a different use case.
Is your concern of out of security, like you don't want different pairs of communication use different keys?
Yes.
You mean the symmetrical key used by the IPSEC kernel stack? Or which key you are talking about?
I'm less interested about the key. I'm just that you won't have the same the same key used for all the tunnels. So if you have, like, say, Pepsi and Cola working on the same hypervisor, and if you're encrypting all the traffic for them between the servers, you have a shared encrypted key for all the traffic, and you don't have a dedicated key for each tenant.
Well, it's certainly a different perspective that we hadn't considered.
Yeah.
Yeah, we can discuss more
Yes.
about this offline, yeah.
And for the Rashid questions, is the vendors, the SmartNIC vendors looking on doing the encryption in the hardware? So yes, we do.
Okay.
Let's thank our speaker one more time.